Okay, guys, it's time to begin. And I just want to show you what's due tomorrow night. This is homework 6, and it's going to cover what we do today on chapters 10 and 11. Now, it says right here the lecture is going to do 11 and 12, but we're actually one chapter behind right now. So we're going to be doing 10 and 11 today. So let's start. So chapter 10 is about the best way to take a survey, a sample, to estimate some population parameter. So we take a sample to find out about, sorry, I got to touch this mic better. Can you hear me well now? Okay, so we take a sample to find out about a larger population. We don't usually have the resources, the time, the money, the energy to sample the whole population, so we take a small sample and use it to make inferences about the larger population. So obviously, the closer the sample resembles the population, the better our inference will be, the more accurate it will be. So the goal is to have the sample be as like the population, to be as much like the population as possible. And that probably sounds familiar to you because we talked about that in reference to picking a treatment and control group that were as alike as possible, with the goal there being to determine causation. Now here the goal is extrapolation. We want to be able to extrapolate from our sample to the larger population. So we want it to be as alike as possible. So this is going to be very familiar to you because we're going to use the same method of randomization for the same exact reasons, to make our sample as much like the population as possible. So this is going to be this chapter is basically a review of what we did before when we were talking about experimental design. Now we're just talking about sampling design. So the terminology, we've talked about this before. We take the small sample from a larger population and to make an inference, to extrapolate from our sample to the population. Now, in the population, we call the numerical facts that we want to find out parameters. And you can remember that because parameters and population both start with a P. And we refer to statistics as those estimates of the parameters that we get from our sample. So we have sample, stats, and population parameters. And these we denote with Greek letters. And these with Roman letters. All right, so here's the main idea, of course, that the sample should be as representative of the population as possible. So let's think about these following methods of sampling and think which one is the best to achieve our goal of having it be as much alike as possible. Okay? So one way to do this is to actually have the researcher hand-pick the sample to make it look as much like the population on all the characteristics that he thinks would be relevant to what he's trying to find out. So, for example, if the population is 50% female and 50% Democrat, then he makes sure his sample is as well. Well, the key here is hand-picking. We saw this before, whenever humans deliberately select something, they introduce bias. Now, as a first step, this is good. Similar to blocking, as a first step was good in experimental design. But the last step should always be randomization. Okay? So it's good as a first step. Okay. I mean, there's a lot of problems with this. One is, that it's been shown over and over again. There's very famous examples where no matter how large the sample is, if the researchers at the last step is, even within certain broad demographic categories, if you allow the poller or the pollster to select within those categories who they're going to interview, there tends to be bias towards richer people, like if they're going door to door, fancier houses, fancier neighborhoods. It tends to introduce tremendous selection bias. Okay? So it leads to bias. All right. Now, these self-selected samples are very, very popular, especially on the internet. You go to a certain website and cast your vote for something. And these are terrible. These are the worst. Because why do you think? Who do you think goes to these websites? People who feel most strongly about an issue. And sometimes they're meant more, sometimes are actual push polls that are meant more to influence public opinion than to reflect it. Because, I remember when, the chief is still a big issue here, but when they were in the process of deciding whether to retire the chief or not, there was tremendous push polls on both sides. Just saying, go to this site, if you're for the chief, or go to this site if you're against the chief, to show how strong your feelings are about this. And they're just reflective of the people who, they're really often used to promote a particular issue rather than to find out how a population actually feels about something. Okay? So these are the worst, and they're tremendous selection, self-selection bias, right? So there's a huge selection bias. I mean, for example, Fox News will say go to their site, so people who watch Fox News will go there and vote a particular way. People who feel very strongly about an issue go there. And it doesn't, no matter how big the sample is, that bias won't go away. So it's a huge selection bias, and these are often used to promote positions rather than reflect how the population feels about them. Okay? So the best way to do it, and we've seen this before, is a probability sample. And the simplest one is just simple random sampling, where every single person in the population has an equal chance of being chosen. And this was done for a long time using random digit dialing, but now people don't answer their phones. So it's become a big problem, but because most people have cell phones, and who in this class would answer if you get a call on your cell phone? Are you going to answer some public opinion poll if it's a survey? Raise your hand if you would. You see nobody here raise their hand. Older people would tend to do it. Like if I asked my mom's, she lives in a retirement home, I've asked the same question, and many older people will still do that just because they're used to it. Even on their cell phones will answer public opinion polls or survey questions. So one way that they get around this probability sampling, I mean, they still try to do it, but sometimes they weight people's opinions more who are less likely to pick up the phone. There's a lot of different types of probability sampling that they're using now. And if you want to read more about it, you should go to Nate Silver's blog about it. But right now, what we're basically, even if you're using these really complicated methods of probability sampling, we're still going to figure out margins of errors the same way as if you were doing a simple random sample, basically. So the methods that we're going to look at on how to make confidence intervals and how sure we are of our estimates are going to be the same, even if they do more complicated probability sampling. All right, so this is the best. I'm introducing some planned introduction of chance into it, and it eliminates selection bias. Okay. So now so here, random samples are best for surveys for exactly the same two reasons that randomized controls are best for experiments. Basically, the first reason is, as we said, that it eliminates selection bias, right? It works, human judgment introduces bias. And random selection is most likely to make the sample as like the population as possible because it eliminates selection bias. We say this over and over again. You see, with enough, this is the key, with enough subjects, random differences average out. First of all, not only on the characteristics that the researchers has identified as relevant, but on all characteristics. So with a big enough sample, these accidental differences average out, whereas with biased samples, it doesn't. The bigger and bigger the sample, you just bigger bias. It doesn't average out. It always goes in the same direction. So it's not. This is very important. And also, these random samples can be translated into box models so that we can use statistics to measure the accuracy of our estimates. Okay. So we have a way to measure, not only do a point estimate, but measure sort of the wiggle room around that, how sure we are that our estimate's correct. Okay, so they eliminate selection bias, but there's still other sources of error. And I just talked about this one, the non-response bias. Random selection eliminates bias in who's chosen for the survey, but not everyone who's chosen responds. That's the big problem. They don't respond. And the problem is you can't just say, oh, I have a small sample. Not many people are responding because the people who respond are going to be different than the people who don't. So even if you increase even if you try to reach out to more people, you're still going to have that same non-response bias. So what they do, researchers try to reduce this by weighing the responses of people according to the difficulty of obtaining their response. Okay, so young people like you, they might, if somebody does answer, if a young person does answer the survey, their response is going to be weighted much more than an older person. And then this is very important too, response bias, and we'll see this all the time. We'll do some experiments in this class where I'll give you different phrasing of the same question. You'll see if it makes a difference in your responses. So, for example, certainly on issues that people feel very emotionally about, like death penalty or abortion, phrasing of the question really influences the response. I mean, if you ask questions about abortion as phrased as a woman's right to choose or killing an unborn baby, you're going to get very different responses. So that's pretty obvious. And so this is the basic idea, that there are lots of sources of bias, right? But even if they were all eliminated, our estimate would still be likely to be off due to chance error. And what this chance error is, this is the standard error that we're going to be using our formulas for standard error for the average and the percent to measure the chance error. So here you have this estimate right here, and this estimate is given by your sample statistic. You'll have an estimate, whatever, so this is a statistic estimated from the sample. Oh, I'm so sorry. Yeah, thank you for telling me. So this is your sample statistic you're going to use to estimate your population parameter. So this is the population parameter. And now there's going to be bias, and that's what we try to reduce by random sampling. So we reduce as much as we can but you're still left with this chance error. And it's we're going to call it a margin of error. This is because every time you take a sample, it's the luck, depending on the luck of the draw, you're going to get a different group of people, right, with different responses. And so we're going to measure this chance error by our standard error formulas. So we can calculate this using our standard error formulas. And that's what the next chapter is going to be about, called confidence intervals here. All right, so the advantage of probability sampling is that we can calculate the likely size of the chance error using box models, probability models. So that's what we're going to be doing, and that's on the next page. All right. So inference and confidence intervals. All right. This is a very important topic. You're going to see confidence intervals all the time. You see it all the time every time you pick up a newspaper and they give you a margin of error. And all the pre-election polls, it will say, plus or minus some margin of error, usually about 3% you'll see for one candidate or the other. So how do they arrive at that? Okay, so this chapter deals with inference, drawing conclusions about a population from what's known about the sample. Now, so far what we've done is gone in the other direction. We've known the exact composition of the box or the population, right? In gambling, we know exactly what's in the box. That's our population. Think of it that way. And so we can calculate the likelihood of all possible outcomes. So we used it to say, what's the probability of getting this possible outcome or that possible sample, right? But now we're going to go in the opposite direction, which is much, much more common. Usually we have a sample because we take a sample because we don't know what's in the population. In fact, the only time that we're in the other situation, generally speaking, is gambling games, games of chance where we know the odds are very well defined. Usually we're in the situation where we don't know the population. We find it out at the election, like in a pre-election poll, we'll finally find out how the population voted. We take the poll because we're trying to predict or estimate how they're going to vote. Okay? So we just see one sample or maybe a few samples, and we use it to estimate the composition of the population. So here's a good example. So in April, an ABC poll of 1,002 randomly selected adults nationwide. Assume they were chosen as a simple random sample. So that's what we're assuming. Okay, out of all U.S. adults. So here, your adults nationwide, that's your population, and this is your sample size. So you're choosing 1,002 out of the millions of adults across the country, and ask them this question, a yes/no question. Do you or does someone in your house own a gun? And this is true, 47% said yes. So this was the sample. So here, let's set up a box model first, just so you get this clear. Okay, so we have so the box now, we're going to make a big box, and we're going to be randomly choosing from the tickets inside this box. So what would be in here? There'd be millions of tickets in here, one for every adult in the U.S., and one for each U.S. adult. Okay, now it's a yes/no question, right? So we're going to represent the yeses as ones and the no's as zeros. So these are the yeses, and these are the no's. So you assume people have either a gun or not in their house, right? We just don't know these. We don't know these percents. I'm going to call this as P for percent in the population. And this P, and then this would be what? If this was P, whatever, they have to add up to 1 or 100%, right? So I'll just say this is the fraction of ones, and this, then 1 minus P would be the zeros, right? And this we don't know. This is 1 minus P. We don't know this, and this is the population percent. Maybe I should write this somewhere. So, okay, destination 1. Okay, so the reason I'm not using the Greek and the Roman letters here is, I mean, this would be a rho and a P, and they look so much alike that it's difficult. You know, rho would be the Greek P, and then you'd have a P, and it would just look they'd look almost the same. So instead, what statisticians usually do is for samples often, another way instead of using the Roman letters is just to put a little hat over it, and that means the sample. So that's the sample percent, okay? And then I'm going to say P is the population percent. Just because it would get too confusing otherwise. And you're going to see that a lot. Either you can put a hat on it or use a this is very commonly used. The hat just means from the sample. Okay, so this is what it looks like. And then what are we doing? We're going to sample. What's our sample size? So from this box, we draw, there's our sample size, n equals 1,002 tickets, right? Now, usually in gambling games, we draw with replacement. But here, do you think we don't want to sample the same person twice. You don't want to call the same person twice. So after you've sampled somebody, you throw, it's without replacement for all surveys. Okay? It's really only gambling games that you would probably do with replacement. So now, also for gambling games, you make it for a single draw, right? Because the box doesn't change. The population doesn't. Here, this represents, you draw the entire population in here. Just imagine that's what you're doing. All right, for a simple random sample. All right, so this is what we do, and what do we get? And then we got this sample percent equal to what? Where is it? 47%. All right, so that's what we know. So if you're going to estimate the percent of all Americans in the box who would answer yes to this question, I mean, you're just going to use this as your point estimate. This is your point estimate. And so that's what else, it's pretty obvious that that's what we would estimate to be this P right here. Okay? Use that to estimate. What else would you use, right? Okay. So, but now we want to put some wiggle room around that, right? Every time we draw, are we going to get that every time? No. If we did it again and drew a different sample of 1,002 people, we're going to get a different population, a different sample percent, right? If we did that over and over and over again, we'll get lots of different sample percents. And they'll follow the normal curve, right? Because that's the central limit theorem said that. But we're getting ahead of ourselves. So now, remember this to get the standard error. What's the standard error? This is what we're trying to do here. The standard error of the percent of ones in n draws. Okay, so this is the sampling error, right? And it depends on two things. N, which we know, our sample size, we know that's 1,002, but also the standard deviation inside this box. Well, we don't know that. We don't know that. So that's a problem with it. There's two problems. One is that we don't know the standard deviation of the box, and that's what we're supposed to use right here, sigma, right, or P, not P hat. And also that this formula is based on drawing with replacement. And our surveys are always without replacement. So how's that going to affect our estimates here, our sampling error? How is it going to affect it? So what we're going to do, what you might expect, is we're going to use our sample SD as an so we're going to use our sample SD as an estimate for our population SD. That's what we're going to do, and that's what we're always going to do. Try to use the sample SD. And so let's do that, okay? So remember that the standard deviation of a 0, 1 box, sigma, right? This is the true population standard deviation, is going to be equal to the square root of p times 1 minus p, right? The 1 minus 0 in front of that, you know, this is exactly the same thing as this, applied to zeros and ones, right? Where p is the proportion of ones in the box and 1 minus p is the proportion of zeros. Same as our usual formula, right? So now we don't know this. So what are we going to do? We're going to estimate that. We'll estimate sigma, that, by what? By the standard deviation of our sample percent. Which is equal to what? The square root of p hat times 1 minus p hat. Okay? So that's what we're going to do. And notice how our standard deviation is directly tied to our mean. Our mean is 40. The mean right here is 0.47, and it's directly tied to the mean. So that's what we're going to do. And so that is the square root of 0.47 times 0.53, which is very close to what? This is like a 50-50 box. 0.5 times 0.5 square root of 0.25. It's very, very close to 0.5. 0.499. Okay? So that's what we're going to use in this formula right here. Right? We're going to put that right in there. All right, let's do that. So our standard error for the percent is going to be, I'll just write it all out, 0.47 times 0.53 over the square root of n, and n is 1,002. And then this 100 is just to change it from a decimal to a percent. So we get 0.499 over the square root of 1,002 times 100, which is equal to 1.58%. And that's, very typical to have a, if you have a 50-50 split about in the population and about a sample size of 1,000, you're going to get this standard error of about 1.5. So how much accuracy is lost in using the standard deviation of the sample to estimate the standard deviation of the box? What do you think? This is really important. Almost none. Why? Because standard deviations of 0, 1 boxes don't vary very much. They're between what? 0 is the smallest it can get, and 0.5 is the largest it can be. So even if we happen to draw a really strange sample, the sample SD will be close to the SD of the box. Unlike, this is completely different than if you're trying to do it, estimate averages. Like if this question was a question, estimate the average, the average family size or the average blood pressure or anything like that, not a percent. Your mean, your average doesn't have any connection to your standard deviation. Here with the percent problem, once we know 0.47, we know the average, which is average of 0, 1 box right here. It's just going to be p. Once we know that, we also know the standard deviation. So they're completely connected to each other. So it gives us a lot of information, whereas, okay? Also, so standard deviations are not going to vary very much. For example, compute the standard deviations of 2 very different samples to see what I mean. Let's say we also got a sample of 50% and 60% ones. Those are very, very different, especially with, with such a big sample size. They're really different. But what's the standard deviation? Let's see, the sample A, SD would be what? That's a 50-50, so it would be 50%, so it would be 0.5 times 0.5, which is the square root of 0.25, which is 0.5. And then for sample B, the SD is going to be what? The square root of 0.6 times 0.4, which is equal to the square root of 0.24. See how they're very, very close? And so this is going to be 0.49. So there's very little difference in that. So we don't have to worry too much about adjusting. You're going to see that later on we're going to have to make an adjustment for when we have problems that aren't percent problems, average problems. We're going to have to adjust our standard deviation and divide by n minus 1 instead of n. And here it's not so much a problem because it just doesn't bounce around very much. So people generally don't divide by n minus 1 here. You'll see that we'll do that later in the hour for a different type of problem. All right, so now, what else? So that was the first problem. So we can be when we have a percent problem, our standard deviation estimated from the sample is a good estimate of our population standard deviation. We don't have to worry too much about that. Now, what about the other problem? That formula was calculated with replacement. So what about how does without replacement change our standard error? Well, there is actually a different formula for calculating samples taken without replacement. You have to multiply that by this correction factor right here. And you can see that this correction factor, basically you have n minus n, square root of, this big N is your population size and this small n is your sample size, okay? So what would the correction factor be in the above example? Well, in the above example, we had such a big population. We had millions of people. Our sample size was only 1,002. So this works out to be almost 1, basically 1. So this is, 1. So it doesn't affect it at all. So most of the time, your sample, when the sample size is small relative to the population size, n, the correction factor is very close to 1 and therefore can be ignored. You see, let's look at this. Here's our formula here. There's no n in this formula because this was assumed that we were replacing the tickets. So it didn't matter how big how big our population was. Now that we're not replacing the ticket, look at, like if you had just a 0 1 with 2 tickets, you'd be depleted right away. You'd have no sampling error, right? So you have to adjust it. And for surveys where you generally have a very large population relative to your sample size, that adjustment doesn't affect anything. So we can use that same formula, which doesn't have a population large n in it at all. You can think, even if the sample size is as large as 20% of the population, what if it was 20% of the population? So you'd have basically about the square root of 80, right? Which is 9, so it would be about 0.9, which hardly affects the standard. I mean, even if you had as much as 20% of the population, it would only reduce your variability by about 0.9. The idea is that, so unless we're sampling much more than 20% of the population, we don't need to use the correction factor, okay? I mean, think about it. If you sampled the whole population, you'd have 0 variability. You'd always get the same thing. So basically, ignoring this is a conservative estimate. It's saying we're having a little bit more error than we really do. And so we don't have to, so basically, you don't put the correction factor in. Okay, but this is fascinating. As long as the sample size is only a small part of the population, which is usually the case, then only the size of the sample, not the size of the population, determines the accuracy of the estimate. And this is so counterintuitive. People say to me all the time, well, how? They don't trust these pre-election polls because they say, well, how can a sample of size 1,000 determine what a population of millions of people are going, how they're going to vote? That's way too small. How can you do that? Well, they just wouldn't trust it. And so what I say, the best analogy I can give is think of sampling as tasting. You don't need to take more from a large glass than from a small glass to see what a drink tastes like. I used to make these punches for these parties back when I liked to have parties a lot. Giant punches and tried to, with alcohol in them, and huge. And I wanted to make them taste real good, so the women would drink a lot and we'd have a better party. And so, because the men are going to drink no matter what, right? At least in my age group. So I would make these, industrial size big bowls and, put all sorts of stuff in it and then stir it up really well, which is like randomizing, stirring up really, really well. And then I'd only need a tiny little taste, right? Only a tiny little taste. If I drank more, I would be, really drunk by the time the party started. No, but it was fine, right? Just a little taste tells you what the whole thing tastes like. Same as if I had just one glass I was mixing a drink. I'd stir it up and taste it. So think of sampling as tasting. You don't need a bigger taste just because you have a bigger population. All right? So that's what this is about. And now, confidence intervals. Okay. So confidence intervals confuse people a lot. Let me see if we can understand them. So in example 1, we got a sample percent of 47% having a gun in the house. And we calculated the standard error to be about 1.5. It was actually 1.5. Let's just say it's 1.5. So we estimate that about 47% of all Americans, give or take, about 1.5% have a gun in their house. So now the question is, how confident are we that our estimate is right? All right? How sure are we that if we really polled all U.S. adults, we'd get 47% plus or minus 1.5? Okay? So basically, how are we going to do this? We're going to think about what we did already about the probability histogram. Basically, what we're going to think about is we have one sample percent. I'm going to put a little hat on it. But we know something about the sampling distribution of that, of the sample percent. We know that, here, let me just write this down because this is an important concept. We know the sampling distribution from the central limit theorem of the sample percent. What do we know about it? We know it follows the normal curve. So here's a normal curve because the central limit theorem says that the probability histogram for the sample percent, that's the sampling distribution. That's the same thing as the sampling distribution of the sample percent. And the sum and the average follows the normal curve as long as the sample is large enough. We have a big sample here of 1,000. So what does it mean? It means that, remember how we came up with this? We started when we knew the population percent. The population percent is right in the center there. We don't know it. But we know that when we draw samples of size, as long as the sample sizes are big enough, that these little percents, these little separate sample percents, follow this type of distribution with what? 68% of the time, our sample percents will lie in here, and 95% of the time, they'll lie within two standard errors. These are standard errors. That's what the standard units are. 95% of the time, they'll lie within two standard errors of our true population percent. Now, we just see one of these. Like this 47%, well, it might be outside those limits. 5% of the time, it's outside. And it's like a lemon of a sample. 5% of the time, it's going to be out here. We don't know. We only see this one. But we can be 95%, but 95% of the time, it's going to be in this range. So we can say 95% of the time, our sample percent will be within 2 standard errors of the true population percent. So how confident are we that our estimate is right? If we have that standard error, we can say, okay, that's one standard error. That's one standard error. So 68% of the time, we can be confident that our sample percent, this one that we see, is inside of here, because 68% of the samples are when we draw over and over and over again. So we're 68% confident it's in here, within one standard error in either direction of the true population percent. So even if it's on the edge, if we want one standard error, we'd capture it. But if it's out here, we wouldn't. Same here. Like 95, even if it's like right at the edge, right here, if we went 2 standard errors over, we'd capture it. Okay? So that's what we mean by that. So we know that if hundreds of pollsters all took random samples of the same size, asking the same question, about 68% of them would get sample percents within one standard error of the true population percent, P. All right? That's the idea. And 95% of them would get within 2. Because within 2, the z-scores, this is a z. These are your z-scores here. All right? So we can be about 68% sure, right, that our sample percent is within one standard error of the true population percent. All right. So in general, so this is how you can think about it, why we say confidence intervals. Don't make the mistake that some people do that say, oh, there's a 68% chance or 95% chance that the true population percentage is 47%. No, this is fixed. We just don't know it. What we're not sure about, what's changing is our sample. So from our sample, we can say that we're 68% sure within one of the true. We don't. What I'm saying is, don't put 47% in here, in the middle, and say 40. If we took 47, 68% of the time, if we did it again, we're going to get samples within plus or minus one standard error, 47%. No, because our 47% could be here, could be anywhere. All we know is that we're confident that if we go plus or minus a certain amount of z-scores, that measures how confident we are, that we'll capture the true population percent. All right, so this is basically how you should think about it these ways. In general, the interval, our sample percent, which is like 47%, plus or minus some critical value of z that you get off the normal curve, is a certain percentage confidence interval that corresponds to this middle area here. All right, so let's do this z star is called the critical value for the corresponding confidence intervals. So let's find these critical values for different confidence intervals here. All right. So we're going to use the normal table to find critical values of z. All right, so a 68% confidence interval, I'm getting it from this normal curve here. Okay, so I looked 68%, and I said, see, I'm estimating. It's not exactly 1, right? And for 95%, it's not exactly 2. It's more like 1.96, actually. I'm just using 2 because people often, so we can do, that's what people do all the time. If you want to be a little more accurate, you could use 1.96. But we're going to be doing a lot of these estimates in our head, and so people often just round it to 2 because it's easy to multiply by 2. All right? So if, let's say an 80% confidence interval would be what? We'll just round it to 80% to 1.3. And in 90%, where's that? 1.65. Okay, so if we're using this table, you can do that. Of course, so let's write that. So you're just asking how many standard errors are you want to attach to each of these. So, and 90% was 1.65, and here was 2. Okay? Basically because on the normal curve, if you go between negative 1.3 and positive 1.3, it's 80% for this one. So that's all we're doing. Any questions on that? You could also just go to our, if you want to be more accurate, which you probably will be in other contexts, if you just went to our p-value calculator here, you could be more accurate if you want. So, so let's see. We want in the middle area, we want to be, let's say we wanted it to be 95. And then we'd compute the z-score and see it's 1.96. And that's what's often used. Okay? So you can use that. And that's generally, it's just, in class, we're just going to, it's easier for us to use 2 so we can do it in our head. Is that okay? All right, and so if we wanted to get a middle area 68% confidence interval, what will it say? 68, and then we'd compute the z-score. Now this is, see, it's very, very close to 1. So for an 80, I bet it's going to be like 1.29 or 1.28 instead of 1.3. Yeah. Okay. These are just the R commands. If you're, at some point, we're going to be doing some bonus problems with R. Okay, so that's the idea. Any questions on that? Okay, so now let's go back to the document camera here. And so 47, okay, find 90 and 95% for the true population. Okay, so we can do, let's do a 95% confidence interval. Is equal to, it's always equal to, I'm just going to write it down this first time so you know, it's equal to your sample percent p hat plus or minus this critical value, right, that corresponds, now with 95 we're going to say, you could say either 2 or 1.96 if you want, times our standard error for the percent. Okay, so in this case, we said this is going to be 1.5. We're just using this rounded number here. So we'd say, to make it really simple, we'd just say 47% plus or minus 2, so we can do it in our head here, times 1.5. And by the way, this is where that plus or minus 3% comes, because for some reason, that's a very conventional percentage that margin of error that people accept. They say plus or minus 3% sounds good. And so they sample about 1,000 people, and that's what it gives you. So it's 47% plus or minus that. And so that would be our lower limit. What do I mean by this? I say you put your lower limit first, and you're going to have to do this on your homework. So your lower limit is 47 minus 3. So that's 44. And your upper will be 50. So that's your confidence interval. The lower first and these are percents because we're doing a percent problem. Any questions on that? And the 90 would be the same way, except instead of putting 2 in here, you'd put 1.65. So 90, so that would make a smaller confidence interval. You know, look, if you're 95% sure, you're going to go way, if you want to be 100% sure, you're going to have a big, big confidence interval, right? So if you're only 90% sure, you're not going to have as big a range. And to which population can you apply the confidence interval to? Well, do you think you can apply it to all adults worldwide? 47% of them have guns? No. I'm sure in China, there's probably like 2% who have guns, just the military, right? In Australia, it might work, but it can't do it all adults worldwide, that's for sure. How about all adults in Illinois? Well, no, you can't, even though you think, hey, Illinois might be like the rest of the country, but certainly all adults in Massachusetts, probably not. They're probably not going to carry it. In Texas, they're going to have a much higher percentage. So you can't apply it to any particular subgroup within the population. You can only apply it to the whole population that it was chosen from. It was chosen from all adults in the U.S., so that's what it's going to reflect. It's not going to reflect particular subgroups within the population. It's not going to reflect hunters, who are going to have a much higher percentage, right? Or college students, which will probably have a lower percentage, et cetera. Or certainly not to some other population outside the U.S. Does that make sense to everybody? The confidence intervals can only be applied to the population that it came from, not to a wider population or a more restricted one. So that's important, and I think you're going to have homework questions like that too. Now, all right, what are we going to do? Okay, so now let's look at another example. Suppose a random sample of 100 female UI freshmen was taken to estimate the average weight of all. So there's our population. That's our box. And here's sample average is 135 and the sample SD. Okay, first let's just set up our box model just to get the picture. So we have this box here where there's 4,000 tickets inside here. On each is written what? What's going to be, not zeros and ones, on each is written what? A number. On each is written a weight. Right? So all the girls, the 4,000, they have some weight, we just don't know it. And we don't know the average, I'm going to call it mu here. And we don't know sigma, the standard of population. This is our population. What do we know? We draw n equals, here's our n. We never use that number. That's our large n. We're never going to use it. I'm just putting it down here. We're never going to use that because 100 is a small percentage of that. So this is our little n. So we draw n equals, randomly draw, n equals 100 tickets without replacement, but it's not going to affect our stats, this without replacement. I just wanted to show you. And what do we get? We get a sample average. Now, how are we going to write that? We get a sample average, this is sample average, right here, of 135 pounds, and a sample SD, not sigma, sample SD equal to what? 25. All right, so these are both pounds. Now, we're going to estimate, okay, so we use this to estimate right here the average weight of all of them. This is going to be 135. That's our estimate, okay? And then to calculate the standard error of the average, what do we need? So remember, the standard error of the average, it's just like for the percent. It's going to be sigma over root n. We don't multiply by 100, right? We're not changing it to a percent, so we just leave it like that. But we don't know sigma, so what are we going to do? So we're going to use the SD of the sample to estimate it like we did before. So let's do that. So here's the S, so we're going to use this as an estimate for that. And so we get 25 over the square root of 100, which is 2.5 pounds. Okay. Now, we really can't assume that the SD is close to the box SD like we did with Y. Because it's not. Because with, before the SD was always between 0 and 0.5. It couldn't bounce around much. And it was directly tied to the percent. This is not in any way tied to that. It could be 135 plus or minus anything. The 135 doesn't tell you anything about the standard deviation. That makes estimates for averages really harder to deal with. And in fact, they're going to follow a different distribution. The sampling distribution of the mean is going to follow something called the t-distribution if you don't know the standard deviation inside here. And that's where we're going to look at pretty soon, which that's never going to happen for percent problems because of this, because the mean is directly tied to the percent. So you don't have to, it's not going to follow a t-distribution, okay? So that's to come. In case you've heard of the t, you're going to hear about it in 5 minutes. All right. But when the sample size is large enough, and people use all different types of measures of large enough. Let's say greater than 25 here. All right. When the sample size, well, that's what we'll do here. The sample SD is a good enough estimate of the population, SD for our purposes. In the next example, we'll adjust the estimate to deal with small samples, and we're going to use the t-distribution. All right. Now, we can still use the normal curve to build confidence intervals around our estimate of the population average. Why? Because the sampling distribution of the probability histogram, the sampling distribution for X bar, for our sample average, as long as our draws with a large enough number of draws, follows the normal curve, even if the data does not. So we don't have to make any assumptions here about the data following the normal curve if we have a large enough sample, okay? And let's assume we do. So we can use, so this is really important. The central limit theorem is amazing, okay? Central limit theorem. All right, so I should write this down. So let's look at this. Find 68 and 95% confidence intervals for the true population average. So let's do the same thing we did before. So let's write the sampling distribution of X bar, the sample average, that's what we're talking about, follows the normal curve. Pretty closely when n is large enough. And I had to do an arbitrary cutoff here, but there's no reason I picked really 25. It's just because our table goes up that high. All right, now let's look at this. So what do I mean by that? I mean that, all right, so remember when we knew what the average was inside the population? We knew, like in gambling is, we knew. And then we looked at what the sampling distribution, where we took different samplings, how much our sample average varied. And we saw that it varied, it followed the normal curve. So the picture would look like this. You'd have some normal distribution, right? And there you have 0 in the middle, right? 0, 1, 2, 3, -1, -2, and -3. But in terms of an average, right here is mu, right in the middle. And then our X bar could be anywhere. But we know that 68% of the time, X bar is going to be in here. And 95% of the time, it's going to be there, etc. It's the same picture. What's in the middle is some true population average, and what's varying is our sample average. And we just see one sample. And so the one sample we saw had 135. So 68% of the time, it's going to be right inside there. So 68% confidence interval for mu is going to be equal to our sample average, which is X bar, 135, plus or minus, what goes with 68, the critical value will say 1, times our standard error of the average, right? So that's going to be 135 plus or minus 2.5. Okay, that would be it. And a 98% confidence interval would be what? 135 plus or minus 2 times 2.5, right? Which would be what? 130 to 140. And this one's 132.5 to 137.5. All right. So that's the same thing, just for averages. But as I said, with averages, you're in a completely different ballgame than percents, because that sample average that you get is not tied to the SD. So your estimate of the SD isn't as good. So what happens with small samples? So now suppose a random sample of only 16 females instead of 100 is taken to estimate the average weight of all 4,000 UI female freshmen. Now we have to assume the weights of the 4,000 are approximately normal, because our n is not big enough for the central limit theorem to kick in. So we have to make this assumption now with a small sample like that. All right, here we had a sample of what? 100. So now we're going to assume that it's approximately normal. And let's just assume we have the same x bar and the same sample ST. So now we have this. This is really what's hanging us up. If we knew sigma and it was normal, we'd be done. We could just use the normal curve. But actually, when you don't know sigma, the sampling distribution of the average follows a slightly different curve called the t-curves. And this is true no matter how big your sample is. It's just after a while, the t-curves look very much like the normal curve. So we're going to have to introduce the t-curves now. Okay, we have to look at the next page, it says, before we can, yeah. So I have to, okay, so now we're going to have to do something different. All right, so we're going to make two adjustments. We're going to, well, let's just read what we do here on the next page. So we're going to be refining the distribution for small n. So we're going to, with the small sample size, using the SD, sample SD to estimate the population SD is not very accurate. It's likely to be too low, so we make an adjustment. Actually, you can make an adjustment. The key thing is, the problem is we're trying to estimate sigma without any other information about it. The mean doesn't tell us anything about it. So now we're in this situation where we have to make a better estimate. So no matter how big your sample size is, doing this will make a better estimate. But you can see as n gets large, this gets very close to 1, so it's hardly worth doing after about 25. But look, if the software does it for you, if you're using software, as most people are, they're pretty much always going to make this adjustment, because it's what's called, if you square that, it's called an unbiased estimate of the variance. So they would do it with percents, too. You could do it with percents, too. You could do that n-1, but nobody ever bothers to do it there. Okay, so when the sample size is small, so we're going to make this adjustment, okay? Just so I can introduce, it's just a lot of tedious calculations, and I'm afraid you're going to lose the main. The beauty of the normal curve is just so much easier to understand what's going on. So we're just with larger samples, we're going to do it. We're going to use the normal curve. With smaller ones, we'll do this. All right, so we're going to make an adjustment and say we have a little more uncertainty. Our estimate's not good, so we make it a little bigger by a factor of n over n-1. So yeah, if you have a sample size of 3, that's going to make a big difference. But if you have a sample size of 30, it's hardly making much difference. All right, and instead of using the normal curve, now we're going to use these t-curves. Look, curves. There's not just one t-curve. This is what makes it complicated. There's a different t-curve for each sample size. All right? So you should use the t-curves when all of these conditions are met. The most important one, this is what you should think of first, most important is sigma is unknown. If sigma is known, you're never going to even consider it. Sigma is unknown. You don't have another way of estimating it. That's why you just don't have another way. All right? So you should use it when the sample size is small. You can still use t with large n. It's still the sampling distribution. When the sigma is unknown, it's still the sampling distribution of the mean. It's just that it's not necessary. But most software programs will do it anyway, just because for a computer it's no harder. There's an analytic solution for t. It's really simple. It's not like it has to do a lot of calculations. But for our brains, it is. It takes away a lot of the intuitive understanding. And the population is close to normally distributed. Okay? So you have to have a normal, basically, pretty normal distribution. Not exactly normal, but close to normal. Okay? Here's another reason why you never use it for percent problems. That's not even close to normal. Zeros and ones. Okay, the standard deviation, and this is the key one, is unknown. If it's known, well, yeah, you could use Z. Okay, so that is it. And because I hated teaching this so much in Stat 100, I don't hate it so much now, because it would just really destroy intuition, and it was just, I called it what I thought was a dirty name, SNUT. I said small to help remember it, normally distributed, unknown, then use T. And that's like slut, smut, snot. I don't know, it just sounded bad to me. And I just found it distasteful to teach, so I thought it was fun to. And students hated learning it, too, because it's so complicated. You guys aren't going to, I mean, for 200, I think it's fine. For Stat 100, I really didn't like teaching it. All right, but I have to teach it. So there's two differences. Okay, so we use this, and all right. Now, we use T-curves. The T-curves have more area in the tails and less in the center, which means that for a given confidence interval, for a given confidence level, the intervals are wider. Okay? So, T-curves. All right, so how do they compare to the normal curve, just so you can see? So what is this? In these curves, K is the number of degrees of freedom. Okay, so then what are degrees of freedom? Degrees of freedom in this case are n minus 1. With a sample size of 1, you can't estimate a standard deviation, right? You could still estimate a mean, but you couldn't estimate the spread. And we're talking about not knowing, estimating a standard deviation here. So you need at least a sample size of 2 to reasonably estimate, to do anything. With 1 point, you can't estimate a spread, right? So we're talking about estimating the standard deviation here. So we're talking about these degrees of freedom here are n minus 1. Later, when you're estimating a slope, it's going to be n minus 2 degrees of freedom. It's going to change. But right now, when you're just talking about the standard deviation, this is what it is. All right. So this is, all right. So this is actually, right here, these T-curves are really the sampling distribution of x bar when sigma is unknown and the population is close to normal. That's what this is. No matter how big your sample size is, it just doesn't matter with a big sample size. You can just use the normal. Why? Because look at how these T-curves change. Okay, so here's look at this one that's tallest. It has the skinniest tails. Whoops, shoot. It looks like that, this one. This right here, that's the normal curve, okay? Now, this one right here, the one that's most, has the fattest tails, like this one right here. I'll just do the two extreme ones. This one is the T-curve with a very small sample size. See how the curves are, the tails are much fatter? Okay, so that's this one. I just showed this one when K is equal to 1. So that's a sample size of 2 right there. And this one's the normal one. I should have made it, I'll do this. This is the normal one. I'll just put little dots on it. And this is that one, okay? So you can see this one is 20, a sample size of, so that means it's a sample size of 20. This is a sample size of 2. This is a sample size of 21. It's almost indistinguishable from the normal curve. So after a while, you just say, might as well just use the normal curve. So basically, is when n becomes large, you know, by the time it's 25, it's very, very close to the normal curve, especially if you're in this range. If you go way out on the tails, like if you're interested in way out on the tails, then you have to, there will be a difference. But in, you know, in the middle of the curve, it doesn't really make any difference. Okay? So T has fatter tails. And shorter in the middle. So note, when n is large, you know, greater than 25, I'll say greater than or equal to 25, T is very close to normal curve. So we're not going to bother using the T, even though it's really the true distribution when you don't know sigma, if you have a normal population. All right, so now we can go back and do our example. And let's do that. And all right. So what are we going to do here? Calculate the SE plus for the average. We only use this for the average problems anyway. So SE plus for the average is just going to be, instead of SD of the box over the square root of n, or SD using the sample standard deviation as an estimate, we're going to use this to estimate that. That's what we're going to do. So we're going to use SD plus. This is SD of box or sigma. We're going to use SD plus as our estimate. So what's SD plus? So let's do that. So SD plus is equal to, well, here's how are we going to adjust that 25. We're going to make it a little bit bigger by a factor. Basically, if you were going to do it from scratch, instead of dividing, when you take the average, instead of dividing by n, you divide by n minus 1. You take the deviations and divide by, you know, square them, do the same, everything you do the usual way. Instead of taking a regular average and divide by n, you divide by n minus 1. But since we already have this regular standard deviation, we're just going to, and it's already been square rooted, so we're just going, instead of sort of get rid of that square root of, we're just going to multiply it by n over n minus 1. Like we originally are going to have a square root of n. That's going to cancel it out and replace it with that n minus 1. So in this case, it's the square root of 16. N was 16, right? I'm getting that from this. Where's n? Right here. 16. That's where that comes from. Over 15 times 25. Can you even see that? No. So that's equal to the square root of 16 over 15 times 25, which is a little bit bigger than 25. It's 25.8. So that is what we're going to be using right there. All right, so we have 25.8 over the square root of 16, which is 6.45 pounds. So there it is. Any questions on that? Oh, it's tedious. Now use the T distribution, okay, to build the confidence intervals. T distribution. So we want to build, all right, it's going to be the same thing. It's going to have this form. And what do we want to do? To build a 95% confidence interval. Okay, so how are we going to think about it? It's the same exact thing, but now we have a different distribution. All right? We want the 95%, so we're going to have 95% in the middle. And now we just have to find the critical values of T, T star, that correspond to that. So that's going to be T and negative T star, right? It's not going to be 2 anymore. It's going to be bigger because remember, it's compared to the normal curve, it's going to be shorter and wider. You're going to have to go out further. right, to get that 95% in the middle, because it's shorter. So how are we going to find that? We have to look on a t-curve for how many degrees of freedom. Okay, so how many degrees of freedom? We said we just saw it, so that's going to be n minus 1, which is equal to 16 minus 1, which is 15. Now we could either go to our computer, but let's just look at our chart back here. And unfortunately, I didn't find a t-table with the middle area. So you'll see it looks a little different. All right, so here's our t-table. What do we want to do? Just look at, all we want to do is look at this, 15 degrees of freedom. All right? Now what, so hard to put, you see, there's so many different curves. All right, now this just gives us the right hand here. So we want 95% in the middle. So if we have 95% in the middle, that means we want this right tail would be 2.5, 2.5. So this would be a 95% confidence interval, because it's just giving one tail. If we wanted, what would this be? A 98% confidence interval, because you'd have 1%. It has to add up to 100, and this part is, it's just giving the right-hand tail here. So this is a 99% confidence interval. What would this be? 90%, 80%, 50%. Okay, so here we want the 95% confidence interval, and it's 2.13. That's the critical value of t corresponding to 95%. So let us go back. 95%, where'd we go? Sorry. All right, so now, so our critical value is what? This right here, t critical is equal to 2.13 and negative t critical. You just use the, you know, between 2.13 and negative 2.13. So that's what you use. Obviously the positive. You're not going to have a negative margin. So the confidence interval is going to be that. So we'll say the 95% confidence interval is going to be 135. That's x bar right there. 135 pounds plus or minus, instead of 2, it's going to be 2.13, right? 2.13 times the standard error for the average plus, which was right here, this, times 6.45. I'm not going to, and that, when I did it out, it came out to be 121.3. It's a low limit, and 148.7. Now, how would it compare to this, to the 95% confidence using Z? Well, that would be what? 95% confidence interval using Z. This would be the same, but instead of 2.13, we'd have 2 or 1.96 even, if you want to be more accurate. And then instead of 6.45, what are you going to have? Instead of 20, you're going to have the standard 25. You'll have 25, not 25.8, because we're just going to use the SD over the square root of 16. And when I did that, see, it's just instead of SD, usually you would use, instead of the 25.8, you just use SD over that, okay? And so when I did that, using the 2, well, I didn't calculate it out. So how do you think it's going to? How is the above one? Which was going to be narrower? This is going to be, see how this is going to be wider? T is a wider, look, 2.13 as opposed to 2 or 1.96, and plus this has 25.8 and 25. T is wider than Z. And T is always going to be wider because you have more uncertainty. That's what it's talking about. All right, so I guess I didn't do choosing the last part. I'll have to see if there's any homework problems on this. If there are homework problems on this, I'm going to have to extend your homework. I can't remember whether there is because we haven't covered it. But right now it's due Wednesday, and I'll send you an email if we have to extend it. And you'll see it on the calendar. I can't remember if I put this on. We haven't covered it. So this is where we'll start next week. I mean, this is what we'll start on Thursday.